So here,
okay. So Casey was talking a lot about, doing stuff on printed circuit boards and implementing stuff for RF and ADS. And the rest of our conversation today is really going to be about what is a printed circuit board and what more can we do with it. So, first of all, this is the Analog Club. We have a website. If you don't have it already, URL's up here. Please get it from me afterwards if not. From there, so a printed circuit board is more than just circuits. There are people doing a lot with it, right? So you see this art piece here, and this is actually another art piece. And there's just a lot of flexibility that you can bring these towards not only your designs, but just something to translate your ideas into. So what is a printed circuit board? Printed circuit board is, I think we talked about this last time, where it's mechanical support for electrical connections. And what you see here is this is pretty much fiberglass supporting copper layers. And this one in particular, there's 4 layers of copper, and then there's these copper vias that connect each of them. And you're able to make the different connections you need there. So how are they made? So this is David Jones, the EE blogger. He's over here, and he makes circuits, but what he's showing off here is a panel of PCBs. And so that's how PCBs are made. They're manufactured in these giant panels where you put the design on them, and then you punch them out from these huge panels. And then this is just an example manufacturing process by a company called Raymane. And so what you see here is that they spend a lot of time actually making sure it's even going to turn on. It's going to do the testing. And you spend very little time actually kind of putting the design on the board itself. And again, this is a little bit unclear. I can send a reference for this as well. So from there, who's making this stuff, right? Who's making PCBs? So as far as the consumer side goes, there's a lot of different people who do it. I like a few of them because they bring different amenities. So if you see here, you have JLC, All PCB, Next PCB, Off Part, PCB Way, what I consider to be your cheap outs. So these are for the hobbyist people. I really like JLC PCB. They're the cheapest of the bunch. Their PCBs are around $1 a piece. Then you have some of the high-tech people, like Raymane and Rogers. Rogers are really famous for actually the materials. So everybody buys the coolest boards from Rogers, and then they'll actually manufacture your PCB out of that cool material. They do some in-house stuff as well, though. And then Raymane is really interesting because they do ceramic PCBs, which is another thing entirely. So rather than using glass, they'll actually use ceramics instead. Now, the question is, how do you get from a schematic to a board, right? We want the board. So there's these design tools. Casey, obviously here with ADS from Keysight, down there. But there's a bunch of other tools. So Altium is real famous, Australian guys. They have a smaller company called Circuit Maker. PCB Artist, this is my least favorite of the bunch. This is from a company called Advanced Circuits. They're actually one of the manufacturers you saw above, but theirs is proprietary. They don't let you export it to any other format, so you can only make it at their company. So it's a little unfriendly. Then you have kind of your industry giants, which is Allegro and Expedition. Those are by Cadence and by Mentor, which are big CAD people, just like Keysight. And then I consider your more consumer stuff is KiCad and Eagle. KiCad kind of has a tool set, like if you imagine Microsoft Word versus Photoshop, as far as selecting tools, which one is intuitive, which one isn't. That's kind of the difference between KiCad and Eagle. It's what are you selecting? Do you select the tool and then the thing, then the tool? And so those are pretty user-friendly, really. Now, footprints, right? We want something like this on the board, and we have these things that we want to put on the board, right? So you're going to spend a lot of time making these cool shapes for your board, but you don't want to spend your life just trying to draw geometry when you're trying to get circuits out of the thing. So there's also these these footprint suppliers. So you have Ultralibrarian for, again, the consumer people. Quest Parts is something that Mentor does for their tool expedition. And then internal to Altium, they have a lot of libraries built out already. So you have engineers in there doing that job as well. Allegro and Expedition have these kind of built in as well, but Allegro is very well supported, and I really like Expedition, the parts quest. So from there, how are you doing the parts themselves? There's distributors. One of them is down 35. I have bought parts from Monster Electronics, and they have arrived that afternoon. They're fantastic. It's about 100 miles away, which is apparently FedEx. Now, you know how to make a PCB, right? You can go from this guy to this nice thing, where it's all lined. You have everything suspended in fiberglass, and your circuits will last forever. Any questions? Okay, let's talk now about what else a PCB is. We've talked about what a PCB is, how we're going to make it. Now, what else can we do with this kind of stuff? So mechanically, there's connectors, heat sinks, and selectors. What do we mean by connector? When you think of your computer, maybe the device that's the most expensive in your house, you know, RTX and all, what's the most expensive thing in your computer? Graphics card. Yeah. So what you see here is it's got two connectors on it, especially if it's the older one. You have SLI and PCIe. And what you'll immediately notice is that both of those connectors are made out of the card itself, right? One of the most expensive things on cards, on your printed circuit boards, after you get past maybe something like an FPGA, is actually going to be the connector. So your connector is going to break the bank. You're going to easily have connectors on your boards, which are $30, $40. Especially when it gets to as many connections as this, super high-grade stuff that has 60 connections, right? Trying to implement something like PCIe. You'll spend a fortune on connectors on your products, unless the connector's made out of the board itself. Then you didn't have to buy anything. You had to buy, you know, 2-inch by 1-inch of PCB, which is cheap to start. So, like you see, there's two on this card actually, SLI and PCIe. And the computer industry is really great about this. They made the motherboard people buy all the connectors, and then you just snap all your cards into the motherboard, right? Man, all the component people got a steal on this. So what you have is DDR4 is doing the same thing. You have your M.2 slot is doing the same thing. You have your connector here. And what's funny even is that the memory people even implemented their standard this way. So now the standard is enforced and the generation is enforced by the connector because they've moved this notch from generation to generation, which means now you need to interface it the correct way. And again, they've done this all for the connector. And then NVMe versus regular M.2 is also doing this. You see the difference here in how the interface is, and the NVMe is substantially better. So that's all I have to say about connectors. Thermals-wise, this is a huge one. On all of your stuff you're going to put on board, you want to know how hot it's going to get. So what you see here is there's a circuit that's modeling how hot your circuit's going to get. Kind of funny. So you have heat, which is power, right? If you think of things are moving. That's the power of it, right? And then you have your different resistances. So if you send, what this symbol is a current symbol, right? So if you send current through resistors, what's going to be at the top? It's current times resistance, voltage. Yeah. So that's what's being represented here by temperature. So we have ambient. So that's usually 25 degrees C for us, in electronics, fortunately or functionally, for being American still. Then we have one thermal resistance, which is called ambient to something. So I'm just considering this the board. Then we have, that's TH, so that's the temperature of the board itself. Then we have our C to H, so that's from the case to the board. So that's another thermal resistance that has to jump over. And then we have from the case to what's called the junction. And the junction is kind of like the heat sink of the circuit itself, of the IC. And so really, what you'll have on data sheets is it'll say, I don't want the junction to get over this temperature, or I think everything in that chip is dead. So it's really important to stay below that that junction temperature that you see on your data sheets for your ICs. So how do we do this? Well, if you have a printed circuit board and you have your component, right? This is just another look at that same circuit, right? Ambient's down here, your board's here, case is this whole black box probably. You can also call it the package. And what we're going to do is we're going to put vias underneath it. So he's got this nice fat solder paste right here, right? And that's a lot of surface area, and it's metal. And we pretty much consider that connected directly to the case. And so what we're going to try to do is we're trying to make that thermal resistance less and less. We're trying to reduce these two terms. We're kind of stuck with this term, right? The junction, so the chip itself to the case, we're stuck with that. So we want to reduce everything else in here. The board to ambient is going to be controlled by surface area. So we want to get as much surface area attached to the chip as we can. And then the RCH, right? If you think of it, fiberglass, not very conductive, right? For temperature and for electric, right? So we really want to put metal underneath it instead. So that's what we're going to do here, is we're putting metal underneath it by putting a bunch of vias underneath here. And the side bonus to that is that now on the other side of the board, we have this huge space of metal connected directly to our chassis, our case, for our IC. And so on the other side of the board, this is what you might see. And really, you can see the connections here, the tabs here. So the chip would actually go on top here. On the other side of the board, you have kind of the same via form, is what we call it. And that's kind of like an embedded heatsink into your PCB itself. All right, one last topic is the selector. So the selector is this idea that you have voltmeter, but there's a bunch of other people who use it. And the other thing that's expensive, besides just the connector to things, is you have your user inputs, right? Your switches, your toggles, all those kind of things. So we don't want to buy those either. We're going to use the PCB again. We're going to use the PCB, and what you see here is that there's just these little tabs, and they just put a little force against the PCB. And as you twist those tabs, they're making a different set of connections here. And so you're able to get a connector which can do all these different modes from just different traces on the PCB connecting through these pieces of metal that are just making contact with it. So you didn't have to buy it. All you need to do is make sure that this top stays firmly against the PCB. Now you don't have to buy connectors. Yes?
So did you take apart the multimeter to get the picture?
No, I found this on Google Images.
Oh, okay.
I had to search long and wide. Not many people have done this, unfortunately.
Right.
Yeah.
So that would be an expensive picture.
It would be, you know, God bless those who do it. Hopefully it wasn't a very expensive voltmeter.
Right.
But, you know, they have good practices though.
Right.
So maybe it was.
Dave Jones does that. Dave Jones does that.
Oh, nice, nice. Yeah, you need to blog. All right, any questions? I think that's all I have to say about mechanical stuff. Great. So if you're interested in more of it, there's this Carl guy on YouTube who makes motors out of printed circuit boards, which is really something. My personal favorite is he has a fire starter, also made out of printed circuit boards. So something to keep in mind. Circuits can do that too. All right, now we're going to talk about the electrical section of printed circuit boards. So, parasitics. I didn't put any parasitics on my board. Why do I have it? There's this idea of lumped models, which again is a very RF concept. And what you have is resistances, capacitance, and inductances on your boards. And just like you have components, these also exist made physically from the things you have on your board. Just the geometries themselves can do this with materials. And what I'm going to do here is I'm going to describe how we can make these with printed circuit boards, and hopefully you get kind of an intuition about which ones you should care about. So the first thing I'm going to talk about is these are my implementations, right? So I'm going to make resistors like this, capacitors look like this, and my inductors are going to look a little swirly. So let's talk about something called a serpentine resistor. We have our material, right, and resistance is given by this factor here, very 302 equation. So the resistivity times the length of your wire, and then you have the thickness of that copper trace and the width of the trace itself. Now, T is really given by your choice in copper. So on printed circuit boards, you usually have 1 ounce, half ounce, and 2 ounce copper. And that copper thickness will tell you how thick that T is. And it's basically given if you had a meter long board by meter long, then hey, you'd have 1 ounce of copper. Now, length and width, these are completely under control. You're doing that drawing right there, right? When you're drawing in one of those pipette tools, Eagle tools, you're drawing in 2D. And so those are your 2D dimensions that you're drawing in. So from that perspective, we need to go back to these guys, the guys who are making our boards. And we need to see how small we can make these geometries. And what you see is that this one's 90 microns. This is how close they came together. And then we have this guy here, which tells you how thick we can actually make it, right? So if we wanted to make a resistor just out of a wire, then we could say, okay, there's nothing that says we can't make it as long as we want. We know it's going to be as thick as we make it based off of our choice in copper. And then we can make the width, this W here, very small. We can make it 90 micrometers. So with that in mind, we can get what turns out to be out of 100 millimeter board, if you just run one trace across, you can get half an ohm. It's nothing, not nothing. Now, I'm going to steal something from the chip guys, and I'm going to use what's called a serpentine resistor. So serpentine, I'm going to run a trace from one side board, and I'm going to make a turn, and I'm going to bring it to the other side board. And I'm just going to do that over and over again on that same layer. And that way, I can make a resistor in series, right? So I'm getting bigger lengths. And they use this out of polysilicon, which is a super resistant material in chips. We don't have that, we're stuck with copper, but we can still do the same practice and get more and more resistance. So if you do the calculations and you go back and forth enough, what you'll end up with is you'll have 0.1 ohms within a millimeter squared area. Not nothing, but that's what you can get on boards. So what about our other elements? Capacitors. So the most basic capacitor you'll see is these parallel plate capacitors. So this is, again, back from our manufacturer. We're told what the dielectric of the fiberglass is, right? And we have this area. Again, if we draw something in 2D, these are the 2D dimensions we can make. And if we go back up now, again, back to these guys, ask, okay, if I ask for a 4-layer board, 4 layers is kind of the point where it becomes super expensive if you want to do 6 layers or above. So you usually stay at 4 layers for designs when you can. Keysight definitely has some stuff that needs more than that, just a few things. But if you're making boards, this is kind of the cost differential. It's boards that use 4 layers or less, and boards that do much, much more. And so in this case, we're trying to be economical. So we're going to make capacitors out of 4-layer boards. And if you do that, there's a capacitor right there, right? We have 2 metal layers, and then there's the dielectric in between, this 2313 material. So that's only 0.1 millimeters, right? So this D is very small, right? Parallel plate capacitor equation is area over distance, and then just the electric constant. Then we have another one, right? So if this is positive, negative, if this one's positive again, now we have 2 capacitors, and they're in parallel, so they add. And we can do this on the 3rd layer as well. So if this one's positive, negative, all 3 capacitors are in parallel, and we're able to get 0.8 picofarads out of any millimeter squared area on a board. So not nothing again, right? We can actually get a decent amount of capacitance, especially for RF people. That's a lot of capacitance, actually. Power, not so much. Power needs a lot of capacitance in the microfarads. So this is probably not what they're looking for in power, but in RF, this is pretty cool. Now, spiral inductors. So inductors, you saw them from Japanese course, Wurzelander's course, 411. You have the solenoid equation, right? So if the spiral goes forever and ever, this is how much your inductance is. So it's the depth of that spiral, the area of the loop, and then your number of turns, and then your magnetics constant. So there's a better way of looking at this, and it's described in depth in Thomas Lee's paper, which is a RFIC guy, and he talks about these different geometries you can use and these different ways of looking at those three or four geometries. And what we have is this equation called the modified Wheeler, and it describes basically a much better way of looking at this model. So we don't have a lot of depth, right? This is why we can't use that Solomon equation, is that we actually don't have any depth at all in this, right? You're assuming that the PCB is flat, right? And that the material doesn't have a crazy amount of depth even, right? Maybe 36 microns for 1 ounce copper on your PCB. Now, if you look at that then you have these different geometries, and you can make spirals out of that in one layer. So here's some constants in the K's over here for that modified Wheeler equation. And what you can end up with is that these people have made these calculators online where if we enter our requirements again, so we want a diameter that's 10 millimeters by 10 millimeters. We're going to choose which of these we want to look at, and we're going to just plug in our minimum sizing from that resistor equation again. And what we get up with is 32 microhenry of inductance from that 10 mil by 10 mil area, the 10 millimeter by 10 millimeter, I should say. So that's a sizable amount of inductance. Now we've looked at all three of these, and so with that 10 millimeter by 10 millimeter area, we can either get 10 ohms of resistance, 80 picofarad of capacitance, and 32 microhenry of inductance. Which of these do you think we care about? Which of these is sizable? Which of these is huge? It ends up being the inductor. Yeah. So inductors, capacitors, you can kind of look at them on the same scale. When you say pico here, you can kind of think of that as pico or nano in the inductor range. And then vice versa, the resistor is a very big unit. And so usually we're looking for maybe kilo ohms, right? Where in these we're looking for micros and nanos. And so this inductance is actually very sizable compared to these other measurements. And so these are the kind of parasitics you really need to worry about when you're laying out your boards. And if you ever see yourself making a board and you see a shape like this when you're laying stuff out, just know you've got a lot of inductance right there. All right, well, thank you all so much.
Thank you. What's your favorite PCB designer?
As far as PCB designers go, I am a big fan of KiCad. So if you look at these other guys, I haven't gotten my hands so dirty with AES, but as far as general purpose, not just RF, you do have a power module in ADS I've touched on slightly, but KiCad, I do a lot of designs, and what you see here is I brought some of my boards over there on that table by the microphone. So if you're interested in looking at some of them, I have things manufactured from Advanced Circuits, JLC PCB, and Allspark available with me today. Any other questions?
Do you get any capacitance if you just put in your that serpentine resistor, right?
Mm-hmm.
Say if they weren't necessarily connected, but you have those parallel lines, you'd still get some capacitance, or is that area too small to make it noticeable? Not between the plates, but on the same surface, right?
Yep, it's on the same surface. So if you think about the capacitor equation, now you have, maybe the best way to look at it is the resistor equation, right? We talked about T being maybe in 1 ounce copper, that's 35 microns. W is what we can make it, and L is what we can make it, right? So we're drawing this on top, and you're asking if we make the area of the capacitor T times L, and then over the W min, right, which is the space between those traces, right, that 90 microns, if that can be sizable. That's actually a way better way to make a capacitor. So this is a very illustrative way to make a capacitor if we look at parasitics, right? This is why I chose this one. But in actuality, if you make capacitors like this, They have really low what's called quality factor because they're resistive still. They have a lot of resistance in series with them. But this is actually a way better way to make capacitors on PCBs. So yes, that's the way you should actually do it. All right, well, thank you so much. I've got a few designs over here if you want to come see them. Appreciate it.